55 gallons is the exact volume held within the interior of a standard industrial steel drum, a container that appears unremarkable yet remains functional for up to 20 years of continuous operation. Why is such extreme longevity required for a seemingly simple object? It would seem that a metal cylinder merely needs to hold liquid without leaking. But in reality, these containers must endure corrosive chemical reactions, internal atmospheric pressure changes, and the physical trauma of repeated impacts while maintaining a hermetically airtight seal. The process of creating a drum of this caliber begins with a strictly regulated manufacturing sequence. It starts with the preparation of raw materials and the mechanical forming of the main body, followed by high-precision longitudinal welding to ensure structural integrity. One can notice how the equipment gradually rolls reinforcing ribs into the steel, providing the necessary rigidity to prevent buckling under weight. But this is just the beginning. It only looks obvious that a cylinder is ready for use once it is shaped, but the engineering demands are much more complex further on. Every unit must undergo a deep chemical cleaning to remove residues before a protective coating is applied to the interior and exterior surfaces. This ensures the steel does not react with its contents over 2 decades of service. The equipment moves the drums along the conveyor at a steady pace toward the final stages of the chain. Specialized sensors and pressurized testing rigs perform rigorous safety inspections on every individual unit before it is cleared for transport. Everything only gets more complicated as the tolerances for these seals are measured in fractions of a millimeter to prevent hazardous leaks. The camera glides along the assembly line where automated manipulators stack the finished products with synchronized precision. One can observe the smooth metallic surfaces reflecting the factory lights as the drums reach the end of the line. The sophisticated engineering systems hidden behind the production process ensure that each container meets international industrial standards. The manufacturing phase concludes as the inspected drums are moved into the storage area for dispatch. The transformation from flat sheets of steel into a high-pressure vessel is complete, and the product is ready to enter the global supply chain. 100 million steel drums are manufactured across the globe every single year. Why is such a massive volume of production necessary for global logistics? It only looks obvious that these containers are meant for one-way transport. But in reality, the demand is driven by a unique engineering cycle where the steel drum serves as a multi-use asset rather than a disposable item, fundamentally changing how industries manage their inventory and shipping costs. This staggering output speed means that nearly 3 new drums emerge from production lines every single second. These units provide critical containment for the chemical sector, the oil and gas industry, food processing, pharmaceuticals, and complex industrial logistics. The process is only gaining momentum as global trade lanes expand. One can notice how the scale of this operation reflects in financial data, with annual market revenue now exceeding $12 billion. This figure continues to climb steadily as the requirement for safe and reliable transport grows on every continent. But this is just the beginning. The steel drum stands out because it is not a single-use product designed for the scrap heap after one journey. Instead, these containers are classified among the most frequently and repeatedly reused steel objects in modern industrial practice. It is visible how the structural integrity of the steel allows for multiple cycles of refurbishing and refilling. Everything only gets more complicated when considering the engineering standards required to maintain this near-limitless cycle of reuse. This capability transforms a basic cylindrical container into an indispensable economic link within the global supply chain. The equipment gradually integrates these units into a circular system that balances durability with cost efficiency. From here, the transformation moves to the next phase of processing as these drums circulate through thousands of ports and warehouses. The material reaches a standard of reliability that allows the global supply chain to function without interruption. 220 to 440 short tons is the massive payload capacity of a single haul truck navigating the depths of an open-pit mine. Why must such immense machines operate in a landscape of constant destruction? At first glance, the extraction of iron ore seems like a simple matter of digging into the earth, but in reality, it requires a meticulously planned sequence of industrial operations to reach the valuable material hidden beneath the surface. Heavy hydraulic excavators begin the process by stripping away the overburden, which is the thick layer of soil and stone covering the ore body. This clearing of the path allows rotary drills to move in, where they bore deep, vertical holes directly into the mineral-rich rock with calculated precision. Explosive charges are loaded into every drill hole with a millisecond delay to ensure a carefully controlled blast. The detonation sound echoes as the solid rock formations fracture into manageable pieces, yet the iron-bearing ore remains structurally intact for the next phase. One can notice how tracked excavators scoop up the shattered material, their metal buckets clanking against the stone, and dump it into the beds of the waiting haul trucks. The process is only gaining momentum. These giant vehicles carry the raw rock away from the mine to the primary crushing station. The equipment gradually reduces the size of the ore using powerful jaw crushers that split boulders with a heavy mechanical crack. The material then passes through cone crushers to ensure every piece reaches a standardized size suitable for the furnace. But this is just the beginning of the metal's origin. It only looks obvious that steel production would rely solely on iron ore extracted from the earth. In the modern industrial landscape, a parallel stream of raw material has become increasingly vital: recycled scrap steel. Old automobiles, discarded household appliances, and dismantled structural steel from urban construction sites are collected directly from their points of origin. Even industrial machinery that has reached the end of its functional service life is added to this collection. Because modern plants aim for efficiency, they incorporate this recycled scrap into their production cycle to work in tandem with the virgin ore. Everything only gets more complicated as the scrap reaches the processing facility. Before entering the refining furnace, the metal is subjected to cutting, shredding, and crushing. One can notice how the machinery breaks the scrap into smaller fragments to facilitate a much faster melting process. This meticulous preparation also allows engineers to maintain precise control over the blending ratio between the recycled steel and the newly produced metal. It is visible how this dual-source system sustains an enormous industrial output while reducing the demand for raw natural resources. The combination of harvested ore and processed scrap ensures a steady flow of material for the next stage of manufacturing. Thus, the raw elements reach a state of readiness for the high-temperature transformation that lies ahead in the refining phase. 150 tons of bundled scrap steel are charged into the deep chamber of an electric arc furnace to begin the process of physical rebirth. Why is such intense electrical power required for this transformation? The metallic mass appears solid and impenetrable at first glance, but the energy of the arcs soon changes its state. Extremely powerful electric currents strike down into the steel mass with a deafening hum, driving internal temperatures beyond 2,700 degrees Fahrenheit. Within just 40 or 50 minutes, the entire load of solid scrap melts down completely. One can notice how the metal loses its shape, transforming into a glowing pool of liquid steel that ripples with intense heat. The process is only gaining momentum. Lighter impurities rise to the surface of the melt like a layer of thick slag once the steel is fully liquefied. Heat-resistant manipulators or automated skimmers move across the surface to remove these waste materials, leaving only the purified metal behind. It only looks obvious to simply melt the scrap, but in reality, the chemical balance must be reconstructed from scratch. Engineers fine-tune the composition by introducing specific amounts of carbon and alloying elements such as manganese, nickel, or chromium. These additives are injected into the liquid to achieve precise mechanical properties for the future product. Everything only gets more complicated as the sensors take control. Digital monitoring systems track the temperature and chemical composition in real time to ensure the refined recycled steel reaches a high level of consistency. This level of uniformity is often superior to the structural qualities of steel produced directly from raw iron ore in a blast furnace. Molten steel is poured from the electric arc furnace into a continuous casting system to begin the transition toward a solid form. The camera glides along the molds where the liquid flows through water-cooled channels. It is visible how the metal gradually solidifies into glowing red square or flat steel billets as the exterior temperature drops. The billets are cut to standard lengths using automated saws once the required level of internal solidity is reached. But this is just the beginning. The metal is transferred directly to the hot rolling line to undergo a massive structural transformation. Reheating units bring the billets to approximately 2,300 degrees Fahrenheit to soften the crystalline structure of the metal. This high temperature makes the heavy blocks easier to shape under the pressure of industrial machinery. The billets pass sequentially through a series of massive rolling mills that stretch the material. Each pass compresses the steel further, making the billet thinner and longer, while it moves progressively closer to its final industrial shape. One can notice how the red-hot metal accelerates as its thickness decreases under the force of the rollers. The steel continues into the cold rolling stage after the initial hot shaping is completed. This specialized process allows for precise control over the final thickness down to the thousandth of an inch. Cold rolling also produces a smoother and more uniform surface finish by eliminating the scale formed during the heating phase. High-quality steel coils are the final result of this mechanical progression. These heavy rolls, each weighing from several short tons to several dozen short tons, are now prepared for transport. The material is ready to enter the steel drum manufacturing plant for the final stage of fabrication. One steel coil, weighing several tons, begins its transformation as it is positioned onto a dedicated uncoiling machine at the start of the production line. Why is such a heavy, coiled mass processed through this specific uncoiling system? At first glance, the task appears to be a simple unwinding of metal, but without the simultaneous flattening of the surface and the continuous feeding of the sheet, the steel would retain its curve, making further precision work impossible. The now flat steel strip moves steadily toward the cutting station, where the drum body will be formed. This is just the beginning. The equipment gradually feeds the material forward under the gaze of automated sensors. An industrial cutting machine drives a high-force blade decisively down onto the steel surface, slicing the metal into individual sheets according to precisely programmed dimensions. One can notice how the blade descends with a sharp mechanical hiss, leaving behind perfectly straight and clean edges. At this stage, accuracy is critical because these two edges will later become the seam of the steel drum body. Any deviation, even by a fraction of a millimeter, would lead to failure. It seems simple to cut a flat sheet, but in reality, the presence of even a single burr can compromise the integrity of the subsequent weld. If the cut is irregular, the drum loses its ability to remain sealed and safely contain its contents under pressure. The process is only gaining momentum. The camera glides along the conveyor as each steel sheet that meets specification is transferred to a rolling machine. This rolling system employs sets of rollers rotating in opposite directions, which simultaneously pull and compress the steel with carefully calculated force. Under this continuous and relentless action, the flat sheet gradually curves inward, its edges drawing closer together until it takes on a hollow cylindrical shape. It is visible how the metal resists at first, then yields to the pressure of the rotating cylinders. Consistency is the primary goal here. The rolling must be uniform along the entire length of the sheet to ensure the drum body remains round and free from distortion. This structural integrity is what allows the finished product to withstand the stresses encountered during real-world use. Everything only gets more complicated as the cylinder moves to the welding station. Automated manipulators align the curved edges for the final joining process. Resistance welding is used to create a continuous seam that is both sufficiently sealed and flexible. One can notice the brief intense glow as the metal bonds at the molecular level, ensuring the drum can safely contain liquids without the risk of leakage. After the weld is secured, the joint is ground smooth to remove any excess material. The process concludes this phase by precisely shaping the rim in preparation for the next assembly stages. The drum body exits the forming station, transitioning into a calm stage as it moves toward the next part of the line. 1,200 millimeters of steel surface move into position once the drum body has been fully welded and hermetically sealed. Why are these flat steel cylinders subjected to further deformation after the structural integrity of the seam is already complete? The central section of the drum passes through sets of specialized forming rollers arranged around its circumference. Without these protruding structures, a thin-walled steel container would lack the structural resistance necessary to withstand the immense pressure of industrial storage and global logistics. Specialized rollers apply controlled pressure from the outside onto the rotating steel surface. One can notice how the metal deforms in a precisely regulated manner as the drum rotates at a steady speed. The equipment gradually pushes into the material to form raised reinforcing ribs that run evenly around the entire body. The rollers exert several tons of force, ensuring that the cold deformation occurs without compromising the molecular structure of the alloy. The positions of these reinforcing ribs are not placed at random. Every millimeter of spacing between the ribs is carefully calculated in advance to distribute forces evenly when the drum is subjected to internal pressure or external impacts. This prevents the steel from buckling under stacking loads in warehouses where containers are often piled several meters high. Everything only gets more complicated as the drum transitions to the next level of structural reinforcement. The drum body continues its journey through an automated corrugation rolling system. This secondary process creates continuous wave-shaped ribs along the length of the drum to significantly increase overall rigidity. It is visible how these waves act as structural bridges, reducing the risk of denting when the drum experiences impacts during transportation across uneven terrain. It only looks obvious that the metal stays straight, but in reality, the drum body must be held in a perfectly stable position by hydraulic grippers. This ensures that each rib maintains a uniform depth and consistent spacing around the full 360 degrees of the circumference. Practical advantages emerge immediately from this increased geometric complexity. The raised rib structure not only makes the steel drum stronger, but also allows it to roll more easily across industrial floor surfaces. These protrusions improve mechanical grip when the drum is moved by hand or gripped by automated lifting equipment. Operators maintain better control over the direction of movement because the ribs act as tracks during manual handling. One can notice how the drum emerges from the station with a transformed profile. Because rib formation directly affects durability, safety, and long-term usability, this step is always regarded as one of the most important stages in the entire steel drum manufacturing process. The material is now ready to move to the next processing phase without haste. 400 tons of pressure are concentrated on a single point during the manufacturing of drum lids and bottoms. These components are produced from independent sheets of steel concurrently with the fabrication of the main drum body. Why must the production of these flat end pieces meet such rigorous technical requirements? The answer lies in the structural integrity of the entire container, as the lid and bottom bear the brunt of internal pressure and external stacking loads. But this is just the beginning of the mechanical transformation. The process is only gaining momentum as flat steel sheets are fed into industrial stamping presses. One can notice how the equipment gradually clamps the material between an upper punch and a lower forming die with zero tolerance for shifting. The punch then delivers a massive force over an extremely short duration of time. This drives the steel into the die, instantly forcing the metal into its final circular geometry. Every cycle is completed in only a few seconds. The pressing force and spatial accuracy are monitored with millisecond precision to prevent any material deformation or microscopic cracking. It only looks obvious that a stamped circle is a finished lid, but in reality, the components are still incomplete. Their outer edges move on to a specialized edge rolling station where the material undergoes further modification. Specialized rollers rotate ceaselessly to bend and curl the steel rim into a predefined profile. This curling operation significantly increases the structural stiffness of the metal and creates the necessary contact surface for sealing. Everything only gets more complicated during the transition to the next level of machining. An uneven rolled edge or a curvature that deviates by even a fraction of a millimeter can directly compromise the drum's sealing performance. For units designed with fill openings, the top lids are diverted for additional precision work. One can notice how fill holes are stamped at exact coordinates and dimensions with high-speed drills or punches. Following this, steel-threaded collars are installed with a press fit to allow for secure sealing. These threaded systems must achieve a perfect fit that is tight enough to prevent liquid leaks while remaining durable enough for repeated opening. This continuous sequence of coordinated operations ensures that every component achieves high dimensional accuracy and uniform thickness. The camera glides along the line where lids and bottoms exhibit a consistent shape and reliable strength. Each piece is engineered to withstand impact and heavy loads under harsh industrial conditions. The material leaves the press, transitioning into a calm stage where it is ready for final assembly. Through these steps, the steel drum becomes a safe and robust vessel throughout its entire service life. Thus, the production of the components concludes this phase, opening the road to the final formation of the product. 100% of the steel drum surfaces must be pristine before the final assembly stage begins. Why is this chemical washing and anti-corrosion treatment performed with such intensity? It seems simple to move straight to joining the components, but in reality, residual machining oils and microscopic metal dust would prevent the protective coatings from adhering, leading to premature structural failure. High-pressure industrial spray nozzles discharge specialized chemical solutions that strip away every trace of surface contaminants. One can notice how the liquid sheets off the metallic cylinders as they transition through the washing tunnels. But this is just the beginning. Separate components meet for the first time on a centralized assembly line. The cylindrical body, the lid, and the bottom were manufactured in different sectors of the factory and now converge with mechanical precision. Automated systems or skilled technicians position the lid onto the open end of the body. Even a deviation of a single millimeter at this specific juncture could compromise the final vacuum-tight performance of the container. It is visible how the components are seated with a faint metallic click before moving forward. The process is only gaining momentum. Rolling machines exert substantial mechanical force to secure the structure. Steel rollers descend upon the pre-rolled edges of the drum, compressing and flattening the metal with thousands of pounds of pressure. This action creates the chimes, which are the tight sealing ridges encircling the top and bottom rims. At first glance, these ridges are merely decorative, but in reality, they lock the lid and bottom to the body with such strength that they can withstand extreme internal pressure. The rollers move at a constant speed, ensuring the deformation of the metal is uniform across the entire circumference. Everything only gets more complicated as the drum moves toward final validation. Sensor arrays and automated inspection systems monitor the production flow without a single second of interruption. These sophisticated sensors measure geometric alignment, the exactness of the roundness, and any potential edge deformation that occurred during the rolling process. Therefore, the internal logic of the line rejects any unit that does not meet the strict industrial standards for sealing integrity and operational safety. One can notice the red glow of laser scanners as they map the surface of each drum to confirm its dimensions. This rigorous oversight guarantees that the steel vessels are capable of transporting hazardous industrial liquids without the risk of leaks in real-world environments. The finished drum body moves toward the final coating station as the assembly phase concludes. 1/1000th of a millimeter of precision is required before the coloring phase even begins. Why is a temporary protective cap fitted so carefully onto the drum opening? At first glance, the interior seems safe once the lid is formed, but without this hermetic shield, microscopic dust, moisture, or foreign particles would contaminate the inner chamber, compromising the purity of the future contents. The process is only gaining momentum. One can notice how the steel drum is conveyed into a fully automated painting facility on a series of rolling metal tracks. Multiple spray nozzles move in synchronized patterns, oscillating with a constant speed to apply an even and controlled coat across the entire outer surface. This paint layer serves more than a visual purpose, acting as a functional protective barrier. It shields the steel from corrosion, ambient humidity, and the harsh environmental conditions encountered during long-distance transport. Everything only gets more complicated as the drum advances slowly into a high-temperature curing oven. Inside the oven, heat and exposure time are tightly monitored by thermal sensors. Metal lays in an even layer as the chemical bond of the coating strengthens under the intense thermal radiation. Once the curing process is complete, the temporary protective cap is removed with a steady mechanical motion, signaling the end of the painting stage. This prepares the vessel for the final inspection phase. Approved steel drums are then transferred to the finished goods warehouse, where the camera glides along rows of completed products. Here, they are neatly stacked onto wooden pallets in specified quantities to ensure maximum stability. It gets more complex further on. Depending on specific transportation requirements, the pallets are wrapped with protective film or secured with heavy-duty tension straps. This prevents any shifting or movement during the high-velocity transit phase. When shipping orders are released, forklifts load the pallets onto trucks or containers, and the drums leave the factory to enter the global logistics network. From regional distribution warehouses to international seaports and major logistics hubs, the journey of each steel drum continues quietly through the supply chain. The manufacturing process concludes this phase, opening the road to formation in the industrial world. The industrial life cycle of every drum is only just beginning. 100% of global industrial logistics relies on the invisible stability of steel drums. Why is this specific form chosen as the primary standard for transporting the most dangerous or sensitive materials? At first glance, the container appears to be a basic metal cylinder. But in reality, the slightest deviation in the thickness of the steel or the integrity of a seam would result in the total collapse of an entire supply chain. This is just the beginning. Manufacturing starts with the selection of raw materials that are governed by strict industrial regulations. One can notice how the sheets move through the line, where sensors detect micro cracks invisible to the naked eye. The steel is calibrated to ensure it can withstand the pressure of chemicals, and the weight of food concentrates during long-distance shipping. The equipment gradually bends the metal into its final cylindrical shape. It is visible how the welding machines maintain a continuous arc to create a seam that is physically stronger than the surrounding metal itself. Every millimeter of these welds is monitored by automated systems to prevent any leaks during transit. Precision is maintained at every stage of the assembly. Components like bungs and lids are manufactured under rigorous safety standards to ensure an airtight seal. The process is only gaining momentum. After the main structure is formed, the drum enters a testing phase where it is subjected to internal pressure that exceeds its standard operating load. It only looks obvious that the drums are simply storage units, but in reality, they act as the silent backbone of the global energy and logistics sectors. Without these containers, the safe movement of materials would be impossible. The manufacturing system functions with such high control that every unit produced is identical to the last. The finished containers are stacked and prepared for distribution across the globe. The metal surface reflects the industrial lighting as the drums move toward the loading docks in an even layer. From this point, the steel drum begins its service as a critical link in the global economy. Thus, the production cycle reaches its conclusion, ensuring that materials move safely from one continent to another.